If you are building agents or fine-tuning vision language models, you really need to pay attention to this architecture. Today, we are looking at Qwen-CUA, native computer use for almost everything, by the Qwen team and Xlang Lab.
Yeah, this one is a big deal.
It really is. So here is the immediate breakdown for you. Qwen-CUA is an agent that operates a computer exactly like a human does. It looks at screenshots, and it outputs raw keyboard and mouse events. That is it.
Right, no hidden tricks.
Exactly. Zero DOM trees, zero accessibility metadata, and zero APIs. Under the hood, it is built on a 397 billion parameter mixture of experts backbone, and it scales all the way up to a 1 trillion parameter max version.
Which is massive.
Right. And to solve the long horizon visual memory problem, they use this rolling window of 20 screenshots, but they fold older ones in fixed blocks to preserve the KV cache.
That is actually one of those elegant parts of the paper.
It is super clever. And they train this on an Alibaba cloud fleet of 100,000 vCPUs using something called soft adaptive policy optimization, or SAPO. The result, state-of-the-art numbers. It hits an 87.6 on OSWorld-Verified, completely beating Claude Opus 4.8 and GPT 5.5.
Which is honestly wild when you consider how it's actually interacting with the machine. I mean,
Yeah.
We've basically been using crutches in agentic workflows for years now.
Yeah, like handing the model a perfectly parsed text file of the screen.
Exactly. You know, like early Web Voyager or those first auto GPT setups.
Yeah.
You pull the HTML DOM or the OS accessibility tree, and you basically hand the model a neat little text-based map of every single button and window.
Right, which sounds optimal until you actually try to deploy it into a messy, real-world production environment.
Oh, it falls apart instantly.
It really does. I mean, anyone listening who has tried to build an enterprise agent knows this. You point your model at some legacy internal dashboard or, a dynamic single-page app where all the CSS classes are obfuscated, and the DOM is essentially just garbage text.
Or think about professional desktop software, right? Like Blender for 3D modeling or a CAD program.
Oh, yeah. Good luck finding a clean DOM in AutoCAD.
Right. There is no DOM. The accessibility tree either doesn't exist or it is totally decoupled from the actual visual workspace. So by stripping all that away and forcing the model to rely purely on pixels and native inputs, Qwen-CUA becomes universally transferable.
It makes total sense. I like to think about it like, it's the difference between plugging an AI directly into a video game's engine code versus handing a robot a controller and making it watch the TV screen.
That is a perfect analogy, actually.
Because the second one, the controller approach, is way harder to train, but that robot can then play literally any game ever made without needing special developer access.
Exactly. If a human can see it and click it, Qwen-CUA can operate it. It's predicting XY coordinates based purely on RGB pixel values. But like you said, handing it a controller and making it watch the screen creates a massive engineering bottleneck.
The visual token explosion.
Right. Vision tokens are incredibly expensive.
Yeah.
If your agent is doing a 50-step workflow, you just can't keep appending high-resolution images to the prompt.
You would blow out the context window immediately, or at least render the inference latency totally unusable.
Yeah, the memory monster is what usually kills these long horizon agents. But Qwen-CUA solves this with a mechanism they call chunked screenshot folding.
Okay, break that down for us.
So they give the agent a strict budget. It can hold exactly 20 active screenshots in its context, no more. Those 20 frames stay in full visual fidelity so the model can track recent UI changes.
But wait, workflows regularly go way past 20 steps. If they are just using a standard sliding window, I would assume that on step 21, the oldest image drops off and the new one comes in, right?
That is what you would expect, yeah. But they explicitly didn't do a standard sliding window.
Wait, really? Why delete 10 images at once instead of just dropping the oldest one as a new one comes in?
It all comes down to cache efficiency and how autoregressive generation actually works. Think about a continuous sliding window. Every time you drop image 1, all the tokens for image 2 through 20 have to shift up one position.
Oh, I see. Which means your entire key value cache is instantly invalidated.
Exactly. You get a cache miss on every single turn.
And for anyone dealing with deployment, the KV cache is what saves you from recomputing the attention matrix for everything you've already processed.
Right. If you shift the prefix, you are forcing a 397 billion parameter model to do a full KV cache rewrite for the entire history. It would absolutely destroy your inference speed.
That sounds computationally disastrous, so moving in blocks of 10 fixes that.
It does. When it hits the limit, it drops the oldest 10 images simultaneously and replaces them with a fixed text placeholder. But here's the genius part. It keeps the text-based reasoning and the actions from those 10 steps.
So it remembers the logic of what it clicked, but the heavy visual tokens are just purged.
Exactly. And because it moves in blocks of 10, the prompt prefix remains totally stable for steps 21 through 30.
Wow. So you just append the new tokens without disturbing the historical prefix at all.
Yeah, it aligns perfectly with cache-aware batched pruning principles. It avoids a full rewrite.
That is just an incredibly elegant way to handle it. You maintain logical continuity without drowning the attention mechanism in redundant pixels.
Right. And keeping inference fast was mandatory for them, especially because of how they had to train this thing. You can't teach an agent to use a computer with static data sets.
Yeah, just showing it pictures of a drop-down menu isn't going to cut it. It needs to actually click and see what happens.
Exactly. It needs an interactive playground. So they built a rollout fleet on Alibaba Cloud using nearly 100,000 vCPUs.
100,000 vCPUs just for generating trajectories.
Yeah, it is a staggering scale. They were running tens of thousands of concurrent environments to give the model that interactive practice.
So what exactly were those environments doing?
They engineered about 40,000 verifiable tasks, broken into 3 main types. The first was synthetic environments, basically mock web services and sandboxed desktop apps, like a fake CAD program.
Just safe places where they could automatically verify if the agent actually did the task right?
Exactly.
Huh.
But the second category is where it gets really interesting. They built user interactive tasks.
Okay, yes. I want to highlight this because this is a standout feature to me. In these tasks, a simulated user basically holds back information, right?
Right. The environment physically does not contain enough data to complete the goal. The agent is forced to realize it doesn't know what to do.
Which is brilliant. It's like training a junior ML engineer, right? You don't want them just guessing and accidentally dropping a production database because a JIRA ticket was vague.
Oh, absolutely not.
You want them to recognize missing evidence, stop, and actually ask for clarification. Training an AI to map visual ambiguity to a pause and query action is just a massive leap for reliability.
It really is. And it stops the agent from hallucinating a path forward. Then, for the third category, they tackled long horizon tasks using something called phase state chaining.
Phase state chaining. How does that work for a complex workflow? Like, say, downloading a data set, cleaning it in Excel, and putting it into a database.
Well, training a 50-step workflow from scratch every time is inefficient, right? The agent messes up step 3 and never even gets to practice step 40.
Right, the trajectory just falls apart early on.
So they break the workflow into verifiable phases. Once the agent successfully finishes the spreadsheet cleaning phase, they serialize that exact system state, the active memory, the file system, the windows.
Oh, I see. So they can basically drop the agent directly into step 40 for practice, rather than waiting for it to randomly get the first 39 steps perfectly right.
Exactly. It lets them verify and train complex workflows incrementally. But that brings us to the actual RL optimization, which was their next huge hurdle.
Right, because even with all this setup, when you run a full 50-step workflow, the reward signal is usually just a sparse pass or fail at the very end.
Exactly. The file is either imported correctly or it isn't.
So if the agent gets a 0, how does the model know which of those 50 specific clicks was the mistake? I mean, standard PPO just struggles so much with that credit assignment problem.
It does. You often end up violently penalizing perfectly good intermediate reasoning just because it clicked cancel instead of confirm on the final pop-up.
Yeah, which just ruins the foundational skills it already learned.
To fix that, they used soft adaptive policy optimization, or SAPO, because the reward only scores that terminal state. SAPO applies a group relative advantage to all the active tokens.
Group relative, meaning they compare multiple attempts at the same task.
Yes. They run a bunch of rollouts.
Yeah.
If the mean reward across the group is, say, 0.5, the trajectory that scored a 1 gets a positive advantage, and the trajectory that scored a 0 gets a negative advantage.
But doesn't that still leave the same vulnerability? A negative advantage applied to a failed 50-step run is still going to degrade the logic from steps 1 through 49.
It would, except SAPO uses an asymmetric temperature-controlled gate.
Okay, asymmetric, meaning the penalties and rewards are treated differently.
Exactly. It decays negative advantage updates much faster than positive ones. It essentially dampens the destructive force of a negative terminal reward.
Oh, wow. That is super smart. You're basically telling the model, hey, you failed the overall task, but we're going to attenuate the penalty so you don't unlearn the basic mouse skills that got you 90% of the way there.
Right. It protects the intermediate logic for these long multimodal trajectories. But SAPO only works if you give it the right tasks to learn from.
What do you mean?
They do this really strict recalibration between training iterations. For every task, they run 8 trial rollouts, and they only keep the tasks where the model succeeds between 1 and 7 times.
Wait, really? Why throw away the tasks that score 0 out of 8? That feels like the exact area where you'd want the model to practice until it gets it right.
It sounds intuitive, but think about how SAP calculates advantage. It compares against the group mean. If every single rollout scores a 0, the mean is 0.
Oh. And then the advantage is 0 for everyone.
Exactly. The loss function just flatlines. You are wasting expensive compute cycles generating 0 gradient. The model is just flailing in the dark.
That makes perfect sense. You need some variance, some successes to show the delta between a good trajectory and a bad one.
Precisely. And on the flip side, if it scores 8 out of 8, the task is saturated. There's nothing left to learn.
Yeah.
So this 1 to 7 rule acts as a Goldilocks zone to maximize the gradient signal.
Okay, so putting all this together, the pure pixel grounding, the chunked context folding, the massive vCPU fleet, and this highly calibrated SAPO setup, what does the final report card look like?
The numbers are incredibly strong. On OSWorld-Verified, the base 397 billion Qwen-CUA hits an 86.2.
Which is huge. For context, Qwen 3.7 was at 73.3 on that exact benchmark. GPT 5.5 is at 78.7, and Claude Opus 4.8 is at 83.4. So they didn't just bump the score, they established a new state-of-the-art.
They really did. And then they scaled it up to over 1 trillion parameters to create Qwen-CUA-Max.
1 trillion parameters
Yeah.
just for operating a computer.
Yeah, and that max version pushes the OSWorld-Verified score to 87.6. Plus, on OSWorld 2.0, which focuses heavily on long horizons, it hits 21.2 on binary completion and 53.3 on partial completion.
Which is where older visual agents usually just completely collapse.
Exactly. The context folding really pays off there.
Yeah. Beyond just the raw benchmarks, there are 2 secondary findings in the paper that tech practitioners are going to love.
Oh, absolutely. The security aspect is fascinating.
Yeah, let's talk about that. Because when an agent relies entirely on reading pixels, prompt injection is a terrifying thought. Like, what if there's hidden text on a web page telling the agent to open the terminal and format the hard drive?
Right. Indirect visual prompt injections. They tested this specifically on the Red Team CUA benchmark, and they found this amazing inverse correlation.
Meaning, as it got better at normal tasks, it got safer.
Yes. The attack success rate, basically how often it fell for malicious injections, plummeted from 36.6 down to 16.4.
That was a massive drop. It seems like that rigorous SAPO training essentially teaches the model to aggressively focus on its verifiable goal state, right? It just learns to ignore weird, out-of-context text because following those distractions never led to a reward during training.
Exactly. It naturally hardens the model against injections. And the second big finding was about efficiency. They tested it on my PC bench and confirmed what we all know. Native UI clicking is universal, but it can be really slow.
Right. If you need to move 50 files, dragging and dropping them one by one is going to eat up an absurd amount of inference compute.
So they allowed the agent to use hybrid tools. They basically gave it access to a standard bash terminal alongside its normal mouse controls.
I love this. It's a true power user. It knows how to use a mouse, but it also knows that sometimes it's just way faster to open the terminal, write a quick bash script, and execute it.
Exactly. The agent autonomously calculates the trade-off. It drastically shortens the trajectories by optimizing for whichever path uses fewer tokens to reach the goal.
That is just incredible. And honestly, it fundamentally reshapes how we should be thinking about the future of software engineering.
It really makes you wonder about APIs.
Exactly. If foundation models can now flawlessly and securely navigate the exact same visual interfaces that humans use, we have to ask ourselves, will the future of software development even bother with building specialized, brittle APIs for AI integrations?
That is a very good question.
Or will we just build graphical user interfaces for humans and simply let the AIs use those instead? It's something to deeply consider as you build out your next stack. Well, that's all for this edition of AI Paper Slop. Catch you on the next one.